Alright, welcome everybody back to another Calcaholic video. My name is Shahvosian and today I'm going to be doing a talk on change of variables under the integral, more specifically polynomial substitution, and then the more generalized U-substitution. So if you don't know already anything about integral calculus, this video is not for you. So what you're going to want to do is go back to my previous video on integral calculus as a whole, so you can learn the concepts like the antiderivative and then the definite integral and such. So let's just get straight into it then. So the general formula here reads as follows. The integral of some function f composed with some other function g times the derivative of g is equal to a much simpler function of u. And if you don't believe me, my claim here, well, let me prove it to you. So what we're going to do is just bring back that left-hand side of that equation, and let's just say g of x was equal to u. So we're going to make that assumption. And then we've got all this mumbo jumbo on the other side, this g prime of x dx that we need to get in terms of u. So how might we do that? Well, if we differentiate this substitution that we made on both left hand and right hand sides, we'll get that du over dx is equal to g prime of x. Now we can multiply a dx to the right hand side, and we'll get du is equal to g prime of x dx. So making all those substitutions, we get that nice simple looking formula, the integral of f with input u. Now, what does this mean? Well, this means that we can make any type of function in this following form into a much simpler integral f composed of u. So I want you to look at this formula here, and I want us to build a strategy for how to select u. And how we do that is, well, notice that g prime of x is a factor of the integrand. So that means that a good substitution should have its derivative be a factor of the integrand. And if that's not, if you're not sure what I mean by that, don't worry about it. We'll get into some examples of such. And I want you to also recall that the constant multiple rule for the integral. This means that constant multiples can be pulled out of the integral operator. Therefore, when making a substitution, the coefficient of the substitution derivative does not need to be a factor of the integrand. Okay, cool. Well, there's another point I want to make. Not every integral can be written in this form. Actually, most aren't. So you might not see some f composed of g where g's derivative is a factor of the integrand. But don't worry. If your integral cannot be written as such, then just a more creative substitution or maybe even a completely different technique of integration is required to solve it. Alright, well, with that being said, let's get into an example here. So let's say we have x squared divided by x cubed plus 1, and this integral is with respect to x. So what do we do here? Well, notice that x cubed plus 1, its derivative is has something to do with this x squared in the numerator. So if I let u equal x cubed plus 1, notice that if I differentiate my left hand and right hand side, oh, something is outputted with an x squared. So that was a good selection of u. Now if I multiply and rearrange my dx and that 3 and take it to the other side, I'll see that a third of the differential u is equal to x squared dx. So I can make all of these substitutions that I've defined here and make this integral equal to a third of the integral of du divided by u. Now, of course, that's an antiderivative. We all know that is a third of the natural logarithm absolute of u plus some integral constant. And I'll recall that u was equal to x cubed plus 1. So we can just make that substitution back. And now we have a final answer in terms of x. So now we can make this conclusion here that the integral of x squared divided by x cubed plus 1 with respect to x is equal to, I'm missing a thirds here. Let me write that down really quick. This is a third, the natural logarithm of x cubed plus 1 with some integral constant c as well. Alright, cool. So now example number 2. This is a nested root problem, and it's not very clear at first what your selection of u should be because there is no choice of u where its derivative is exactly a factor in the integrand. But you can go ahead and make some selections and see what works. And the selection I'm going to make is u is equal to 1 minus the square root of x. So I'm going to continue with what I've been doing up to this point, differentiating the left-hand and right-hand side in hopes of isolating for that differential dx. And cross multiplying over here will yield this. Dx is equal to negative 2 square root x du. Now, do I stop here or do I continue? Well, if I were to substitute in all the information that I know up to this point, I'll get an integral like this, where it's negative 2, the integral of square u squared x du. And notice that this integral is not in terms of u. I have a squared x there, and I have two variables under my integrand. This is not allowed. We're not allowed to have two variables under the integral, because what we're doing is, of course, a single variable integral. We can't integrate with respect to two variables, so what do? Well, if we go a little bit further and mess around with the substitutions we made, we'll see that if we move around some of the terms, we'll see that square root x is equal to 1 minus u. So then this over here, if we just directly substitute square root x for this thing in terms of u, we'll get that dx is equal to negative 2, 1 minus u du. So now if we make all of those substitutions to our integral, we'll get the integral of square root u times 1 minus u all times negative 2. And that is allowed. So let's go ahead and distribute that square root of u into my 1 minus u. And we'll get the integral of negative 2. We'll get negative 2 times the integral of u to the power of 1/2 minus u to the power of 3/2. All with respect to u, of course. So let's bring that up here. And let's just use the reverse power rule on both my terms here. And we'll get negative 2 times 2/3 u to the 3/2 minus 2/5 times u to the 5/2. Plus some integral constant c, of course. So now let's just distribute those negative 2's inside, and we'll get this expression here. And I want us to bring that up here and recall the substitution we made, which was u equals 1 minus the square root of x. So let's go ahead and make everything in terms of x again, and just directly substituting that back in. And now we can make the conclusion that this nested root integral is equal to this fat expression over here. All right, cool. So now I want to talk about general substitutions. Everything we've been looking at up to this point has just been polynomials, but polynomials are just a very specific type of substitution where the change of variable, or what we've been using up to this point being the letter u, is set equal to some polynomial expression. However, that's not always the case. Substitutions do not have to always be polynomial. This is why we use the umbrella term U-sub when describing substitutions under the integral as a whole. And actually, most of the integrals given in Calc 1 and Calc 2 are solved just using some type of substitution. So now I want us to look at an example where the integral we're dealing with, the choice of u, is not going to be polynomial. Over here it's going to be ln x, and the reason why I choose ln x because I know its derivative is 1 over x, and we can clearly see that this is being divided by x, so its derivative is definitely a factor of the integrand. So letting u equal ln x, differentiating both sides will give me du over dx is equal to 1 divided by x, and I can just multiply that dx to the other side, yielding du is equal to dx divided by x. Okay, cool. So making all these substitutions, I'll get the integral of u squared with respect to u. And just using my reverse power rule, I'll get 1/3 u cubed plus some integral constant c. Alright, cool. This is equal to 1/3 ln x cubed plus c. And I'm just going to bring that up here and rewrite it again. And now we can make that conclusion that this integral is definitely equal to 1/3 ln x cubed plus c. And if you want to verify this, you can go ahead and prove by differentiating left and right hand side, and you'll see that it is exactly correct. But let's just move on to our fourth example. Now we have the integral of tangent x. So how do we go about this? We just have the tangent function. There is no other function to be like, oh yeah, that's its derivative. So what we can actually do, though, is bring back its fundamental definition here in terms of sines and cosines. And now you have two options for you. You can either choose sine or you can choose cosine. But what selection is going to be a good choice of u? Well, let's say we chose sine x to be u. its derivative is cosine. But notice that we don't have cosine as a factor. We actually have secant as a factor, so that wouldn't be correct. Now, what if I choose cosine to be my u? Well, its derivative is some multiple of sine. So, and we see sine x is clearly a multiple, or sorry, a factor in our integrand. So that probably should be a good choice of u. So if I let u equal cosine x here, differentiating both sides will give me negative du equals sine x dx. And we clearly see we have a sine x dx here, so we can make this substitution, giving us the -1 times the integral of du over u. And that's an antiderivative that we know pretty well. That's going to be negative ln absolutes u plus some integral constant c. Alright, now recall u was equal to cosine x, so this is equal to negative ln cosine x plus c. And what we could do is bring that multiple of -1 into the natural logarithm and just as an exponent and just reciprocate the cosine, giving us ln secant x plus c. And now differentiating this, we'd get 1 over secant x times secant x tangent x, and yeah, that gives us tangent x, so we know that is correct as well. Alright, now I want to talk about definite integrals. So far we've only done examples of indefinite integrals. And note that in any type of integral, when you're changing variables, all components of the integral must be in terms of a single variable. So let's say I make x and I substitute it into u. Everything under the integral must be in terms of u. And this includes, when doing definite integrals, the limits of integration as well. And just how I would express this with a formula would be the general formula I showed you earlier, but just notice how now my left hand side has bounds in terms of x and my right hand side has bounds in terms of u. So you also have to account for the bounds being changed. And an example of this, let's go ahead and take the integral of sine 2x times cosine 2x with respect to x being evaluated over the interval 0 to pi over 2. There are many ways you can go about solving this. You can turn this into just sines using a double angle formula, or you can choose cosine x to be u, or you could do what I did, which was choose sine 2x to be u. So now going ahead with this selection of u, I'm going to differentiate my left and right hand side and rearrange the terms and get du divided by 2 is equal to cosine 2x dx. We see we have a cosine 2x dx as a factor in our integrand, so we can go ahead and just make that substitution. But notice that I also have to account for my limits of integration. So if I go ahead and plug in 0 for x, where I have u equals sine 2x, I'd get u equals sine 0. Sine 0 is 0, so my bottom stays 0. But now notice that if I plug in pi over 2 to my substitution, I have u equals sine pi, and sine pi is also going to be equal to 0. So I have this integral going from u equals 0 to u equals 0. And we know our properties of definite integrals. If I'm integrating over a point, the area is going to be equal to 0 because points have no width. So that means that this integral as a whole is going to be equal to 0. And you see how that substitution there, taking this in terms of u as well as the bounds, made this problem really easy because we were just integrating under a point. Now I want to talk about one more property. It's the definite integrals change of variable property, and all this really means is that if I change variables under a definite integral, the choice of like the letter itself, u, v, t, whatever I choose, typically called the dummy variable, and then the substitution itself does not impact the calculation. So the evaluated area will be equal to each other, of course, because we've defined them to be equal. But this is very important when you get problems like this. So I have the integral going from -1 to +1 of 1 divided by e to the x to the 5th plus 1, all with respect to x. So now there's no clear selection of u here, but taking into account of the dummy variables property along with that, at every point of my substitution, those areas have to be equal to each other. What I can try to do here is get a integral that looks very, very similar to the integral I'm working with. And you'll see what I mean here. If I let x equal -t, that means that dx is going to be negative dt. What about my bounds? Well, if I plug in -1 for x, t is going to be +1. And if I plug in +1 for x, t is going to be -1. So this means my bounds just switch, and then I get a -1 outside there from the differential. And using that negative sign, we can actually swap the bounds back to regular, like so. And so now you see that we have a very, very similar integral. So similar, in fact, using that dummy variable property, we can just make this integral in terms of x again, because the letter we use does not matter. We'll see that these two integrals, the one we start with and the one we're at right now, are very similar. They have the same bounds and the denominators are almost identical. So what happens if we add the integral on the left-hand side to both sides of this equation? Well, we'll get that twice this integral we started with is equal to the integral that we started with plus the integral we have right now. And the goal here is to combine these under one integral operator. And how we'd do that is to get the right-hand side, this integral right here, to have the same denominator as over here. And we can easily do that by simply just multiplying that integral by e to the x to the 5, and the numerator and denominator. Notice now these have the exact same bounds. They have the exact same denominator. We can combine them into one integral. And when we do that, we're going to get the integral from -1 to +1 of something that just simplifies to 1. So let's go ahead and also divide or multiply by 1/2 on both sides. And this is going to give us that this integral that we wanted in the beginning is equal to 1/2 of 1 minus -1, which is of course equal to 1/2 times 2, which is equal to 1. So now we can confidently conclude that this integral that is crazy, it's non-elementary actually if there weren't bounds, is equal to 1. And how do we do that? Well, we abuse the fact that at any point the letter that we choose to substitute does not matter. And we also abuse the fact that at any point in our substitution, it is still equal to the original integral as long as we made the substitutions correctly. And that's all the examples I really want to give today. I think that should give you a pretty good understanding of how U-Substitution works as a whole. So I'm just going to thank you for watching. And if this video was helpful to you at all, please consider subscribing. It would mean a lot. And yeah, everyone have a good day. I'll see you in the next video.